In this video, we're going to go over section 11.6 from our textbook, which is on polar equations. So first, we're going to talk about rectangular and polar coordinates. So if a point has rectangular coordinates x comma y and polar coordinates given by r comma theta, then these coordinates are related as follows with these equations here. Now, looking at this diagram here, this P is in rectangular coordinates here, and this P is in our polar coordinates here, where r here is going to be the distance from our pole or from our origin, and then this horizontal component here is going to be our polar axis. Now r is going to be the magnitude of this guy here, and then theta is going to be our angle from this polar axis here. So let's look at an example. We want to plot this point and then find the rectangular coordinates of that point using this information here. So the first thing that I'm going to do, we have our unit circle here, and our unit circle is in terms of radians. So first I'm just going to convert our 240 degrees to radians. If you remember, we can do so just by multiplying by pi over 180. This tells us that in radians, this measure is 4 pi over 3. Okay, so we want to plot this point. Now remember, 4 pi over 3 is this here. So our ray, 4 pi over 3, from the origin is pointing in this direction here. Now, something to notice though, let me write it down here. Our r in this case is minus 7. So this tells us this point that we're trying to plot is going to be 7 units in the opposite direction of our ray, 4 pi over 3. So this tells us our point is actually going to be somewhere over here. So we're just going to draw a ray that's in the opposite direction of our 4 pi over 3 ray. All right, now, actually plotting the point, we know that the distance from this origin here is going to be 7. We've already taken into account the minus here by drawing a ray in the other direction. Now, just this magnitude needs to be 7. So this is our polar coordinate plane here. So these circles just represent exactly that, just the distance from our origin. So we have 2, so this should be 4, 6, and 8 here. So this would be the distance from our origin right here would be 8. So this point we're going to plot right about there. And the last thing we want to do for this problem is find the rectangular coordinates of this point. And we'll do so using this equation and this equation here, and plugging in our known values for r and theta. So we know x is going to be equal to r times cosine theta. So this will be minus 7 times cosine of 4 pi over 3, or 240 degrees. So this will be minus 7, and then cosine of 4 pi over 3, going back to our unit circle here, is going to be minus 1/2. So our x-coordinate is just going to be positive 7 over 2. Now similarly for our y-coordinate here, we're going to plug in our known values. Now sine of 4 pi over 3 is going to be minus root 3 over 2. So we'll get a positive 7 root 3 over 2 in this case. So this in rectangular coordinates is going to be 7 over 2, comma 7 root 3 over 2. All right, let's do another example. In this case, we want to plot this point, and we also want to give 2 other pairs of polar coordinates for the point. So first we're going to plot this guy, and then we'll do that. Again, I want to write theta in radians here. We have negative 210. This is going to be the same as minus 7 pi over 6, just converting this to radians like in the same way that we did for the last example. Now notice minus 7 pi over 6, let's go back to our unit circle here. Since we have a negative angle, we're going to start here and we're actually going to move in our clockwise direction here. So starting here, going to minus 7 pi over 6, we end up right around here. Now notice we could also rewrite this with a positive angle. Instead of moving in this direction to account for our negative angle here, we can start here and move in a counterclockwise direction. So we can rewrite this as a positive angle. So starting here on our x-axis, we can move in this direction, the same radian measure away from our horizontal axis as minus 7 pi over 6. Now doing so, we would end up right here at 5 pi over 6. So minus 7 pi over 6 is the same thing as 5 pi over 6. Now what we can do is plot this in the same way that we did for the last example. So our ray for 5 pi over 6 is going to be right about here. And then we know our radius is going to be 4. So this point is going to be right here. All right, and then we also want to give 2 other pairs of polar coordinates. So these will be equivalent coordinates. So just alternate ways to write this here. Now we just showed actually that r theta is going to be the same thing as this guy over here. So one pair of equivalent polar coordinates could be 4, 5 pi over 6. And if we wanted to write this in degrees here, this would be 4, 150 degrees. Now, another set of equivalent pairs of polar coordinates would be if we just added one full rotation to this. If we added 360 degrees to this point here, we just do one full rotation and end up right back at this point. So, an equivalent pair, we'd still have our radius as 4, then we just add 360 degrees to 5 pi over 6, or 150 degrees, and we'd get 510 degrees. All right, let's do another example here. For this point here, we first want to plot the point, give 2 other pairs of polar coordinates for this point, and give the rectangular coordinates of this point. So the first thing we'll do is plot this guy, just like how we did for the last 2 examples. So our theta is going to be pi over 4 here. So our pi over 4 ray is right about here. And then r, in this case, is going to be 3. So this point here is going to be right about there. Now for part B of this question, we want to find 2 other pairs of polar coordinates for this point. So the first one we can do just by doing what we did for the last example, adding one full rotation to our original pair of polar coordinates. Doing so, we'll get this here, and this will be an equivalent pair. Now, just by the same reasoning as the last example, if this is our point and we just add one full rotation to it, we're still going to get that point there. Now, something to notice in this case, r is positive, and our theta is actually in between 2 pi and 4 pi. Now, it could be the case on the homework where they want you to stick to these parameters, but it could also be the case where they ask for something different. What if you wanted to find equivalent polar coordinates where r is less than 0, so negative, and theta is going to be in between 0 and 2 pi. Now, in this case, we're going to have to employ some reasoning that we saw in the first example. Now, if you remember, let's go back to this example here. Looking at theta, we had our original ray here for 4 pi over 3. Now, since our radius was negative, this point is going to be 7 units in the opposite direction of that ray. So what we had to do was go in the opposite direction and plot our point on this ray here. So if we use this same reasoning, we could start with the ray in this direction here. That ray would be 5 pi over 4. It's in the exact opposite direction as pi over 4. So if we started with this ray, and then we said the radius were minus 3, what we'd have to do is we would start with this ray at 5 pi over 4, and then since the radius is minus 3, the distance from the origin would be 3 units in the opposite direction of this ray here. So let's just write that in a different color. This would be our 5 pi over 4 ray. And if our radius was 3, we would have to be 3 units in the opposite direction of this ray, which gives us this point. So that tells us that point would be an equivalent pair of polar coordinates. And that would be minus 3 and 5 pi over 4. And in this case, we satisfied these parameters here, where our radius is negative and our theta is going to be in between 0 and 2 pi. All right, let's do the last part here. We want to give the rectangular coordinates of this point. So we'll do so using the fact that x is going to be equal to r times cosine of theta, and y is going to be r times sine of theta. So here we know cosine of pi over 4 is going to be root 2 over 2. And similarly, sine of pi over 4 is root 2 over 2. So in rectangular coordinates, this will be 3 times root 2 over 2, and then 3 times root 2 over 2 for y as well. All right, so let's do another example here. In this case, we're given rectangular coordinates. First, we want to plot the point and then give 2 pairs of polar coordinates for this point. So we have this point 4, 0, and this is our rectangular coordinate system here. Plotting this point, x is going to be 4 and y is going to be 0, so our point's going to be right about there. Now for part B, we want to give 2 pairs of polar coordinates for the point. So we can use the fact we know that x is equal to 4 and y is equal to 0 in this case. If x is equal to 4, then this tells us 4 must be equal to r times cosine theta. And similarly, if y is equal to 0, then 0 must be equal to r times sine theta. We also know from these equations up here that r squared is equal to this guy. So what we can do is use what we know for x and y to find r. So r squared is going to be equal to x squared, which will be 4 squared, plus y squared, which is 0 squared. So this is going to be equal to 16. This tells us that r then is going to be equal to plus or minus 4, because what we're doing is we're taking the square root of both sides. Now this leaves us with 2 possibilities here. R is equal to 4, or r is equal to minus 4. Now if r is equal to positive 4, then we're going to use these 2 equations here. 4 is going to be equal to 4 times cosine theta, and 0 is going to be equal to 4 times sine of theta. Now what we'll do is we'll solve for sine and cosine theta, so we can divide by 4 on both sides for both of these equations here. Doing so, we end up with cosine theta being equal to 1. Similarly, on this side, we end up with sine theta being equal to 0. So we need cosine theta to be equal to 1 and sine theta to be equal to 0. Well, this only happens when theta is equal to 0. So one pair of polar coordinates for this point would be 4, that's our value for r in this case, and 0 degrees, our value for theta. Another point will occur when r is equal to minus 4. And then actually, sorry, before we do that, I just wanted to go back to our original point in rectangular coordinates here. Notice that our radius, our distance from the origin here, is 4 in this case. That's what we see here. And if we're thinking about this as a unit circle or in our polar coordinate system, this would be 0 degrees at our polar axis here. So just something to, just an observation there. Now going back to our other option for our radius, -4, we'll do the same thing here. We know x is equal to 4, and that'll be equal to r times cosine theta, so in this case, -4 times cosine theta. And 0 is going to be equal to -4 times sine theta. Now doing the same thing, we're going to solve for cosine theta, so we're going to divide both sides by -4 for both of these equations here. Doing so, we end up with cosine theta being equal to -1 and sine theta being equal to 0. Now in this case, this will happen when theta is equal to 180 degrees. So this tells us another pair of polar coordinates for this point, which would be -4 in this case, since r is going to be -4, comma 180 degrees. So those would be two pairs of polar coordinates for this point here. All right, so let's do another example. Kind of switching gears a little bit. In this case, we want to convert this here to a polar equation. So we have x squared plus y squared is equal to 100. Well, as we saw in the last example, r squared is going to be equal to x squared plus y squared. So that means r squared must be equal to 100. Now solving for r here, take the square root of both sides. So this tells us r is going to be equal to plus or minus 10. And that would be our final answer here. And so this ends up actually just being an equation of a circle with center at radius 10. And that's given by this graph here. So we just have a circle with radius 10. Something like that there. All right, let's do a similar example. Now we want to convert this rectangular equation to a polar equation, and then we're going to express r in terms of theta. So first we have 8x plus y is equal to 10. So this means 8x, which is r times cosine theta, plus y, which is r times sine theta, is equal to 10. So we have 8r cosine theta plus r sine theta is equal to 10. Now notice we have an r in both of these terms. So we'll pull that guy out. We have 8 cosine theta plus sine theta. It's going to be equal to 10. And then we'll divide by 8 cosine theta plus sine theta on both sides of our equation here. In doing so, we'll get r alone. We have r is going to be equal to 10 over 8 cosine theta plus sine theta. So this will be our polar equation in terms of theta. Now, the last thing we're going to look at is graphs of polar equations. So equations such as these guys here are examples of polar equations where r and theta are going to be the variables. Now, in order to graph these guys, what we're going to do is we're going to evaluate r in terms of theta until a pattern appears. So this is going to be our strategy for graphing. And then this here on the right is a table of the different types of polar graphs here that we'll see. And then in the book and on the PowerPoint slides, it goes into a little more depth of these guys and their naming conventions. All right, so let's look at this example here. What we want to do is give a complete graph of this polar equation and identify the type of polar graph. So, like I said, what we're going to do is evaluate r in terms of theta until a pattern appears. So, unfortunately, what we're going to have to do is just plug in a bunch of different values for theta. And I did that here for us already. So plugging in a bunch of values for theta to see what r is, we get this here. Now notice a pattern does appear. After pi, we start to see repeated values. So it looks like on this side of our x-axis here is going to be reflected on this side of our x-axis. So what we'll do here is we'll plot these points and then see what type of figure appears. So first we have 0, 14. So that point is going to be right about here. Next we have pi over 6 and 13.1. So pi over 6 is going to be somewhere over here. And again, this is just going to be a rough sketch. But pi over 6 is somewhere over here. And so 13.1 is probably going to be somewhere right there. Next point we have is pi over 3. So that ray is right about here. And this point will be 10.5. So 10 is right here. So 10.5 is maybe right around here. All right. Again, we have pi over 2. So we have pi over 2 comma 7. So that point will be right about here. Next, we have 2 pi over 3 and 3.5. So 2 pi over 3 is right about here. And then we'll have 3.5. So maybe this point there. Then we have 5 pi over 6, which is going to be this right here, is 0.94. So that's going to be right about there. And then at pi, we have 0, so at the origin here. Now this is where the points start to repeat, and we can see a reflection across the x-axis. We know at 7 pi over 6, it's going to be 0.94. That ray is about there. And we said 0.94 is about here. So repeating this, I'm just going to reflect all of these points over our x-axis here. Now connecting these points, we end up with a shape. Try to make this as nice as possible. That's kind of similar to this here. All right, and then going back to this table over here, that shape looks kind of like this guy here. So this will be a limicon. Sorry for my pronunciation. But specifically, it'll be a cardioid. And then, like I said, the more details on these graphs here and the naming conventions and whatnot are in the PowerPoint slides and in the book. But we do have this interesting shape here for this polar equation. All right, so that'll be it for this video.